They're going to be looking at Chapter 17, Activity 2, primarily on the Diels-Alder reaction today. So last activity, we spent a lot of time drawing out resonance contributors for both dienes and dienophiles. And we noted that sometimes the diene will have a delta negative at the bottom carbon or sometimes the top carbon. So it does vary, but we primarily care about the end carbon, so either this one or this one, right, for the diene. And then the dienophile it's pretty much always the furthest carbon away. So you can draw resonance contributors, and it's good to be able to do that. You can't actually draw them with this particular case with the CF3. There's no p orbital on this particular electron withdrawing group. But even though it only withdraws through induction and not resonance, still the electrons move towards the fluorines. So the carbon with the least electron density, be the one farthest away. So once you figure out which one has a delta negative and a delta positive, right, then you need to make sure those are aligned. And sometimes that means flipping one or the other over, and usually we just flip the dienophile over since that's easier. It can be easier. And then if they're aligned, they will have an electrostatic attraction that lowers the energy of the transition state during the Diels-Alder reaction, leading to a faster reaction. Okay, so we want to make sure that we have the charges aligned, right, and that will give us the correct regioisomer. So if we had drawn out what we would have gotten from the mismatched case, ignoring stereochemistry, we would have gotten this one. So if you can think about what might be the relationship between these two, right, these are actually related as constitutional isomers. Hopefully you've heard that term before. Constitutional isomers are isomers with the same molecular formula, but they have a different atom connectivity. Okay, so basically the CF3 is connected at a different carbon atom in the ring. So they are constitutional isomers, and we also sometimes call those regioisomers. Those terms can kind of be interchanged. So when we say the reaction is regioselective, what it means is that it's selective for one potential constitutional isomer over another. And that just means that this one is produced in greater than 50%, one is produced less than 50%. Okay, so another example of regiochemistry is something like a Markovnikov reaction. You might recall, I've done this many times, a hydration of an alkene. It will give you the Markovnikov product, and this is a major product. And then also it would give you a minor product that we typically don't usually draw, which we might call the anti-Markovnikov product. So these two compounds are related as constitutional isomers, right? But this is major and this is minor in this reaction. So this reaction is said to be regioselective, right, producing the Markovnikov product as the major product. So we've seen regioselectivity before, right? You haven't seen it completely defined as just favoring one constitutional isomer over another in a reaction. That's what it means. Okay, so I'm going to take a second to switch to a different screen. Hopefully many of you have seen this. I must have too many screens open. I must have closed it. Now it's open, and now I should. Okay. hold on. Are you guys seeing the Diels-Alder handout or no? I'm not seeing that.
Yeah.
You are seeing it? Okay, I guess I found it out. Okay, so I just wanted you to know that I uploaded this. It's in with the activities, and it's a step-by-step guide for figuring out the product of a Diels-Alder reaction.
Well, we're seeing activity 2.
Oh, okay, you're seeing.
Is there a different one?
Yeah, I'm wanting you to see what I'm seeing.
Oh yeah, we don't see it on your screen.
Okay. Here it is. Found it. Now do you see it? Yes. Okay, good.
Yeah.
All right. So step 1 is confirmation, right? So we have, if you're ever given the diene in an S-trans conformation, you need to switch it to S-cis. So if it's already given in an S-cis conformation, you can just move to step 2. Right? Step 2 is what we've been talking about, this regioselectivity. And in order to figure out if you need to care about regioselectivity, you're going to look for planes of symmetry. So analyze both the diene and the dienophile for a potential plane of symmetry. And you need the diene to be S-cis to see it, if it is there. And as long as one of those two has a plane of symmetry, then there will not be a possibility to form regioisomers. There's only one, because if you flip one over, it's the same thing, essentially. You don't need to consider regiochemistry. That makes it easy if you find this plane of symmetry. But there's the case where you don't see one, right, in either the diene or the dienophile. And in that case, you need to consider regioselectivity. So that means you need to figure out through resonance contributors, where is the delta negative, where is the delta positive, and make sure they're aligned to give the major regioisomer. Okay, and then we'll move on to stereoselectivity eventually. We haven't really gotten there yet. Back here. So much stuff on my screen. Okay, so that's the idea. So we want to draw the product here, right? And we're going to go through the first 2 steps because we're ignoring stereochemistry. Okay, so once we add that in, we'll introduce that 3rd step as well. So we're looking for, first step, check to make sure the diene is in an S-cis configuration, and it is. So then we look for a plane of symmetry. They don't have one in the diene, but there is one in the dienophile. That means you don't worry about regioselectivity. You can just combine them as drawn. Okay? And so when you do that, you are basically going to be forming sigma bonds between the terminal carbons on the diene and the alkene carbons of the dienophile. So we would just sketch out a cyclohexane ring, right? Because we always get that. And then there'll be an alkene here. And notice on this carbon, there's both a methyl and a dimethylamine. So we need to draw both of those in, methyl and the dimethyl. And then the dienophile was actually the cyclic structure itself, right? So we can draw in an attached ring here. For that, okay. Is that okay with everybody? So we're just combining them. Of course, we did form 3 new stereocenters here. So when we are considering stereochemistry, we will need to put dashes and wedges there, but not for now. So next one, we're looking for S-cis, and it is. Look for a plane of symmetry. I find one in my diene, so no worries for regioselectivity. I can sketch out my cyclohexane ring. I notice that at these carbons, there's methyls. So I should go ahead and add those in. And then the dienophile has at this carbon a methyl ketone. Again, we've got 3 new stereocenters. When we are worried about stereochemistry, we will worry about those. So next one.
Wait, can you show again for that one? I don't see how to like combine it.
Okay, so basically we have the pi bonds shift, one sigma bonds here, and then this one shifts over to form a new pi bond. So basically you're connecting these two in a 6-membered ring. Okay, so if we were to count 1, 2, 3, 4, 5, 6. Because we do 1, 5.
Got it. Would you recommend also like just like counting the carbons like you get on the first one to make sure you don't miss like that methyl group now that's like sticking?
Yeah, double check, you know, what is attached to each carbon. And make sure that if it's a non-hydrogen group, that you account for it here. So numbering is helpful. So next one, it is already an S-cis for us. It's great. Okay, looking for planes of symmetry, I don't find one. So now I have to consider where's the delta negative and delta positive, if there is one. Okay, and so from here, right, you might have to draw out resonance contributors. Basically, this oxygen is going to push electrons to that carbon. So this is going to be our delta negative. And it's always the furthest one away. The dienophile. Right now, these are drawn mismatched, right? So we need to flip one of these guys over. You can imagine, maybe you want to draw it again. It doesn't matter. You could flip the diene over just by convention. We sort of typically flip the dienophile. It doesn't matter. Okay, so this is basically, I took this one and I did a little flip. And I did that because I want my delta negative and delta positive carbon to be aligned. That leads to an electrostatic, basically an opposite charge attraction, which lowers the energy of the transitions. It leads to a faster reaction, and reveals all the reactions kinetically controlled. Faster is better. Okay, so we have them now aligned, right? And it's a little bit more tricky because of the ring here, so now we have to draw a bicyclic structure. But it's not too bad once you get used to it. So typically I kind of start out with something like this. And then because I have a 1 carbon bridge in those two, I'm just going to come up for a 1 carbon bridge. Then my alkene will be here, my methoxy group, the diene is there. And then I can just for the rest of the 6-member ring. So if you can't see that, we could do some numbering. And then so there's no other substituents on these except for the methoxy group and then this methyl. Okay, and that's going to end up. This one is a little tricky because the stereochemistry is shown as sort of going this direction or this direction. And you don't have to show stereochemistry. So technically either would be correct, but I can't bring myself to draw it incorrectly. I'll just tell you it's going to be down. But as long as you had it sort of connected to that carbon in some way, shape, or form, that would be okay. This part. All right, moving on. And by the way, right, these are stereocenters. Sometimes it's hard to see with the bicyclic structures, but those bridgehead carbons, as we call them, are chiral centers. So but the way we draw it actually shows the stereochemistry without any dashes. Okay, next one. Writing a little too big here. So we have these two. The diene is in an S cis. So I can skip step 1. There is no plane of symmetry. Determine where my delta negative, delta positive are, and unfortunately we have to flip again because they're misaligned. So I can just flip this around to, I'm going to draw it closer. That way I can save on space. Drawing out my cyclohexene. I just pay attention to, are there any substituents here? There is methoxy in that carbon, so I'll go ahead and add that in. And then I went ahead and flipped this so that now the nitrile is the end group at the top. So for this one, the diene is given in an S trans conformation. So we need to do an S trans to S cis conversion where we rotate around the bond. So I can just kind of redraw it. It's just 1,3-butadiene. So fairly straightforward rotation there. And then you're going to imagine forming the 6 members in here. We don't have to worry about stereochemistry or regiochemistry because there is an internal plane on the diene. You don't need to really worry about aligning partial charges. Okay. So kind of sketching in the product here. Have that. So in this one, there's only one stereo center in the product. In this one, there's 2. We'll worry about dashes and wedges later. Last one here is we notice that the diene is in an S trans, but unfortunately, we're not able to rotate the single bond because of the ring. There's no way to do that. So when that happens, we just have no reaction. Because it's required in the S cis conformation to react. Any questions on geochemistry? So the idea is to find a potential internal plane of symmetry. If you don't see one, see if there's in the delta negative, delta positive that you need to find. Okay. We are going to start here. And unfortunately, this is not correct. So I'm going to have to do some changing of what it says here. So now we're going to start looking at the stereochemistry of the Diels-Alder reaction. And there's going to be, I'm going to show you lots of pictures. What he has here is kind of very minimal, but we'll go through it in detail so you don't have to memorize it. We can visualize it a lot better. But what we are going to talk about is something where the electron withdrawing group, right? So this is that EWG, electron withdrawing group attached to the dienophile. It actually will prefer what we call an endo position, which means that it's pointed in, right, towards the diene, as opposed to pointed sort of out and opposite the diene. We call this the endo versus the exo transition state. And it will prefer an endo transition state because of something called secondary orbital overlap, which I'll show you a better picture of once we actually draw in some orbitals. But there's a favorable interaction between an orbital on this carbon and an orbital on this carbon. And that leads to a lower energy transition state. The part that's wrong is this part. So this is actually the kinetic product. And this is the thermodynamic. Okay, and the reason for that is the thermodynamic product is always the most stable product. And the bottom structure here is actually more stable than the top structure. And that's because this larger group, right? So this is a hydrogen, this is a larger group. It's pointed away from the larger bridge. If you imagine these are the two bridgehead carbons, right? We have sort of the longer bridge, which I just outlined in blue, right? And the shorter bridge. So stability-wise, it's better if the smaller group is closer to the longer bridge. The larger group is closer to the shorter bridge. It's just going to be less sterically crowded. So this is actually much more stable, right? So it's the thermodynamic product. But the Diels-Alder reaction is kinetically controlled. It's done at a low temperature, and so it doesn't reach an equilibrium. Whatever is formed faster is trapped as the major product. This one is formed faster due to a lower energy transition state because of the favorable secondary orbital overlap there. Okay, so this is just not quite correct. Let's look at some better pictures of what's going on here with the orbitals. So I drew this out for the endo and exo approach for the same example that was shown on the last page. So we have our cyclopentadiene, and then this is the dienophile, which we call an enone. Anywho, I drew in the orbitals involved. And remember that all of these carbons, right, are sp2 hybridized. This carbon here is sp3, but it's not involved in the reaction. And then these, the entire double bond with the ketone here, that's all sp2. What I've drawn in are the p orbitals, which are really not p orbitals. They're the high molecular orbitals we talked about before. But this is the sort of the simplified version of showing them as individuals. So what I drew in was the HOMO of the diene, because the diene is the electron-rich component. So it utilizes its HOMO. It's basically donating electrons, so it needs to use an orbital that has electrons. And then the dienophile is accepting electrons. So it utilizes its LUMO, which doesn't currently have any electrons in it. And so I've drawn a picture of the HOMO and the LUMO of the two. Right? And the HOMO has one node in the middle here, so that's why I changed phases. You can see it's red, red on the top, switch to blue, blue. So change in phase there. Right? And then we have to use the LUMO of the dienophile, which is also a diene. The diene because there's 4 p orbitals all in a row. But it's a diene just like this one, right? And it's using its LUMO, so that's the one higher in energy, and there's 2 nodes. So I switched phases twice. I went from blue on the top, pink on the top, argon, and then blue on the top. So every time you switch phases, there's a node. So if we're looking at what's happening here, and you want to kind of imagine the dienophile approaching the diene from the bottom, right? So we're basically, just because it's a little bit easier to visualize, place the diene, which is planar, because all of these carbons are trigonoplanar, right? So it's just like this planar. And then we move the diene from the bottom, which is also, by the way, entirely trigonoplanar. So it's basically these 2 plates. We're imagining the dienophile sort of swooping in underneath the top plate, if that makes sense. Does it approach from the top? Yes. That leads to the enantiomer. Okay, so when the dienophile, instead of approaching from the bottom, approaches from the top of the plate, that will lead to the enantiomer. So that's always happening. We don't need to draw both of them. So we're just drawing it from the bottom. So what we have here is we're going to be forming 2 new sigma bonds between this carbon, and also this carbon, the two new sigma bonds. So you can see that as they approach the top to bottom, blue lobe will overlap with that blue lobe. This pink lobe will overlap with that pink lobe. Okay, and they're going to start to form a sigma bond. Right now it's p orbital overlap. And it's going to change to sp3 hybridized orbitals and a sigma bond. So it's undergo orbital change as it forms a new bond. Okay, the secondary orbital overlap, right, is this p orbital, not one of the alkene ones, but off to the side on the electron withdrawing group. Okay, there's a p orbital in this carbon that can overlap with the p orbital on this carbon. Right? And that just leads to, it doesn't lead to a new bond. It just leads to a temporary stabilization of the transition state. And then the dienophile will sort of move away from the diene and into the plane. So it's just temporary, it doesn't lead to a new bond, but it helps to stabilize the transitions. If we come over here to the exo approach, I drew the same HOMO and LUMO. Right? And we're still seeing the correct overlap here. We make two new sigma bonds, so blue, blue. But now this p orbital is way too far away in this one to do any kind of overlap. So that transition state isn't stabilized the way the other one was. So that's why we end up with, by the way, this would lead to the more stable product, right? So but this has a lower energy transition state, and the reaction is kinetically. So that's why this is favored. So that's why we say the endo rule, which basically talks about the fact that the electron withdrawing group needs to point in, right? And that's going to be a favored approach. And right, so when we drew in the HOMO and LUMO, we see that these are blue to blue is in phase, pink to pink is in phase, even the secondary orbital overlap. So these are what we call, this is a symmetry allowed process. If they weren't in phase, meaning red aligned with blue somewhere, then it would not be allowed and the reaction would not happen. So we can predict whether or not reactions occur through using molecular orbital theory. That's one of the advantages of that theory. So that's essentially what's happening, right? When we just have this picture of saying, okay, this is a good interaction here. It's really talking about the p orbitals that's leading to that favorable interaction. Okay, and then we move on to more stereochemistry. So he presents this little picture here, right, which you can memorize if you would like. You can go, okay, when they approach, 2 will always go up. And if it's pointed out here, it'll always go down. Right? You could memorize that. But I want to take you through an example that shows you, right, why. Why does this lead to that? Instead of memorizing. Let's go through that with a more specific example. So one thing I wanted to point out before we go through that example is kind of taking it one step further. Remember up here, our endo approach, we had the blue overlapping with the blue, the red overlapping with the red, and those are going to form the sigma bonds. So what does that look like, right, in route to the product? So those p orbitals, right, the blue to blue. So this used to be a perfect dumbbell, right, pointed straight up and straight down. But they change. As blue overlaps with blue, the blue lobe grows, essentially, and overlaps with the other one and forms a bond. So this has now changed from what used to be an unhybridized p orbital, okay, and it's changed to now a hybridized sp3 orbital. So this carbon, that p orbital changed to sp3. So this carbon underwent a change from sp2 to sp. And that now forms this new sigma bond, which is an overlap of 2 sp3 hybridized orbitals, if these carbons are, right, same with these. So that's essentially what's happening is the p orbitals do a top to bottom overlap, and then a rehybridization occurs. The dienophile sort of comes up into the plane with this part, so it can form a 6-membered ring. And we'll do some more pictures as well, okay, on a different example to help you visualize that. I want to take you through an example, sort of from start to end, utilizing the handout. Okay, so let's say you were given this one. You need to draw the major Diels-Alder product. Right, we'll say now we're going to, including stereochemistry. And to help you out, you can follow the handout, although you won't have it on the exam. Okay, so we have, this is our diene, right? This is our dienophile. How do we know that? This one has the electron withdrawing group, right? And this one has an electron donating. And I know it's sometimes confusing to point to an oxygen and say it's an electron donating group, but it is because while it inductively withdraws electrons, resonance it donates electrons. And resonance is more dominant than induction. Whereas this one up here, it withdraws both inductively and through resonance. So it's definitely an electron withdrawal. Okay, so we're going to take you through the steps here in figuring this out, and especially with the stereochemistry, showing some nice pictures. So step number 1, we're given the diene in an S-trans. So we need to flip or rotate to an S-cis. One of the things I like to point out is a little double check. You always want to double check your work, because sometimes it's not as easy to visualize that. Like, it might seem easy in some cases, but other times you might get it wrong. So one of the things you can do is ask yourselves, if you have the 2 alkenes, are they E or Z? Right? Because that shouldn't change. You can't rotate from E to Z or Z to E, because that's rotating a pylon. You can't do that. We already know it. Right? We're only rotating single bond. So if this is, let's say, EE, it should be EE over here. We shouldn't have changed that. If we did change it, we did something wrong. So here we have the 2, this is definitely E, the 2 hydrogens opposite. And then this one, this is a higher priority group than the methyl, right? And then the methoxy is higher than the hydrogen. So these are our priority groups. This carbon and this one is actually. I just want to come over here and make sure through that rotation we didn't actually change. And we did not. Okay. So, or you can just kind of imagine, take this bottom half and flip it over. Draw a mirror image. And that works out. Okay, so if given it in S-trans, you have to rotate S. Step 2, determine if you need to worry about regioselectivity. So when we do that, we're looking for planes of symmetry. I don't have one. So I do have to care about regioselectivity. So through resonance, I determined that this carbon, right, between these 2, these are the ones that I care about. Between those 2 is this top one that has the delta negative. Go ahead and add that in here. And then through resonance, we also figured out that this bottom carbon is delta positive. So as they're drawn right now, they are not aligned charges. So we have to flip it. So, okay. There's 2 potential approaches because there's no internal plane of symmetry, right? And these are the carbons that I care about. They're the red dots. I drew in the delta negative here. I drew this and flipped it over and drew it again. doing the delta positive on both of them. Right, and we say, okay, which one is aligned, right? This orientation where delta negative and delta positive. So this will be the major product, ignoring stereochemistry. And then next step is to think about stereochemistry, because we now have 3 new stereocenters. We want to know what stereochemistry is very specific to all this. We want to know what's happening. We can kind of look at the orbitals, right, involved in the endo and exo approach. So notice how I can draw an endo approach and an exo approach, even with these molecules. So in the example before, the diene was part of a ring. It didn't have any substituents. Now it's not part of a ring and has a lot of substituents. Totally fine. It's the same thing. You just
Can I ask a quick question?
All right, what was that, Shira?
Oh, yeah, just can you review really fast why is that the major product again? The bot.
Okay, so it is because when you flip it over, then the delta positive is here, the delta negative is here, and they're aligned. So if I had thought about the original way, right, without flipping it over, it would be these two, and I would be trying to align here and here. And I would realize that delta negative and delta positive are not going to be forming a bond like that. They need to be, matched to form a bond.
Got it. Okay. Okay.
So because it's like 2 ions. They're gonna form an attraction. So they'll be attracted to one another. Okay. So now that we have the correct, right, orientation. So notice how we decided, right, this is better. This is the correct alignment. So that means that my ketone is pointed down. I know that. Right? So I kind of kept that already over here. It's not up here on this carbon. It is, right? It's the flipped over one. It's on the bottom. And even exo-endo, it's still on the bottom. Right? It's still attached to this carbon, regardless. Does that make sense, Matt? Okay, the difference is now, yes, right, it is on the bottom, but even if it's on the bottom, like this, and not like this, it could be like this, or it could be like this when it approaches. So even with the electron withdrawing group being on the bottom carbon here, does it point in or does it point out, right, when it approaches the diene? And we know that as long as there's a p orbital here, and there is in the carbonyl, and there usually is with most electrons, that there's going to be a favorable orbital interaction, secondary orbital interaction, when it points in. So sort of drawing it this way and this way, that's going to form 2 different constitutional isomers. We call that regiochemistry. But with it pointed down, it can still approach with 2 different orientations. That doesn't lead to this group being at a different carbon, it's still at the same carbon, but it will lead to different stereochemistry when it approaches in or out. And it will lead to one of these to be on a wedge and a dash. Vice versa. A wedge. The dash. Okay, anywho, so this is what we're seeing here. So with it on the bottom, is it going to point in or is it going to point out? We know that it points in because of favorable overlap. Okay, so let's see what's happening. We're going to focus now on looking at carbon number 1 and carbon number 4, right? Because we're having the favorable orbital overlap here. Those orbitals. So we want to see right? Because there's groups here now. There's this methyl, there's this methoxy. Those are going to lead to those groups being on a dash or a wedge. So we want to understand why. So if we look at this picture over here, this is the same diene. I just took away the orbitals for C2 and C3 because they don't matter right now. They're not going to become sp3, so we don't care. There's going to be no dashes or wedges. Like this methyl will still be a regular line. It's not going to be a dash or wedge, so we don't really care. So we're highlighting carbons 1 and 4 because we know that these carbons do become sp3. That means that these groups do need to be placed on a dash or a wedge. You need to know what to do with it. So as these p orbitals become sp3, hybridized orbitals, right? This is trigonal planar and this is a tetrahedron. So they go through a change. And the p orbital essentially elongates on the side because of the orbital overlap. But this C3-C4 bond undergoes a counterclockwise rotation because this p orbital, which is right now pointing up and down, needs to rotate to pointing to this direction because it's going to be part of a sigma bond, right? That completes the 6-member ring. So if I had counted, right, 1, 2, 4, 5, 6. So it's eventually going to be part of a 6-member ring. In order for this to point along this direction, this bond has to undergo a counterclockwise rotation so that the white lobe points this direction. So can you imagine that? The opposite is occurring for C2-C1. It's going to undergo a clockwise rotation in order for this p orbital, specifically the colored lobe here, to point in this direction. That rotates this hydrogen up and this methyl down. This counterclockwise rotation here rotates this hydrogen up, the methyl down. And again, it's doing that because this is pointed up and down right now. It needs to be in the plane going this direction. The other one needs to be forming a bond in the opposite direction. This is pointing down, this is not this way, not the same direction, but opposite direction. So it's going to be part of a ring. Okay, so they're rotating, right? This one had rotated clockwise, this one had rotated counterclockwise in order to get their sigma bond in the right direction. So the groups that were pointed, right, this group that is pointed in ends up because of the direction of the rotation. This group that was pointed out ends up down. We say that these are in because it's sort of in with respect to the diene. So this is another group that's pointed in. It also gets to be up. So notice these are the groups that are pointed in. They both end up on 2 wedges. The groups that are pointed out, right, this is sort of out, end up both down. By the way, I posted this as well. The activity. You can get a copy of this. So that's the reason why, when you go back to the little picture here, that's the reason why, notice these groups that are pointed in, right, end up. These groups that are pointed out end up down. So we don't really have to, I find it difficult to just memorize that. But what I can do easily is remember, if I've got a group pointed in, it will end up on a wedge. If I have a group pointed out, it will end up on a dash. That's easier for me than this 1, 2, 3, 4 crap that I don't like to memorize. Okay, so what's going on with the dienophile? What can we remember about that? These groups are what we call the endo groups. Right? Those are the groups pointed in with respect to the dienophile. Whereas out here, I would call these exo groups. Right? They're pointed out with respect to the dienophile. What do we know about the electron withdrawing group? Any electron withdrawing group will prefer endo. So when we're aligning things, we'll make sure that we understand that that's going to be preferring endo. And that means that like hydrogens or something else, not an electron withdrawing group, will be exo by default. So this worked out, right, that if we can kind of start here, got the endo approach. So as these start to form new sigma bonds, this also rotates, or the entire molecule rotates counterclockwise and into the plane, which is going to leave what's pointed in pointed down. And it's difficult to visualize. Another picture. After they're forming the new sigma bonds. So we had our groups that were pointed in, those are now up positions. Our groups that were pointed out, they're now in the down positions. Down and out. And with the dienophile, the electron withdrawing group, which prefers endo, will end up down. And that's because as the entire dienophile rotates to be part of the 6-membered ring, what was pointed in is now pointed down. So it's like this. Comes in this way, your electron withdrawing group, and then it rotates this way. Okay, and anything that was out, exo, will end up up. So what did we have? How does that simplify over here, right? We don't need to draw in the hydrogen here. We just draw in the methyl down. The methoxy group up. And the electron withdrawing group down. And that's the finished stereochemistry included product where we've drawn the group on a dash or a wedge in the chiral center. The enantiomer also forms, which happens from when the dienophile approaches from the top. When it approaches from the top, everything's still the same. It's just exacting your image, what happened before. So how do you know if you should write plus and minus? Basically, if there is a chiral center, then we need to write plus and minus. And it doesn't matter how many chiral centers there are. So what's cool is that while you do get a mixture of enantiomers, with 3 stereo centers, right, you have 2 to the 3, 8 possible stereoisomers that could form. But you are only going to get 2. Get this one and it's you only get 2 out of 8 possible. The other ones don't form. Hopefully that made some sense. That you can kind of. So we'll go through his little example here at the bottom. So we have the diene is already drawn at cis, but there's no internal plane of symmetry. So he had to look and see where is the delta negative, delta positive. They were not aligned, so we had to flip them over so that now they are aligned. And we sort of think about, okay, is this going to point out or in? Right? It's going to point in. And so that means that it's going to end up down. points endo, it ends up down. And then this methoxy group is pointed out. So it ends up down. And the groups that are pointed in, which are the hydrogens, those will end up. Groups that are pointed out, which is hydrogen. These are the in ones. Right? These are the out is the methoxy. The out groups end up down. In groups end up up, but we don't show those because it's hydrogen. Anything endo will point down. Okay, so that may or may not make sense if we do a bunch of problems. Hopefully, eventually it will sink in. So, and by the way, I'm going to disagree with the key on some of these. And I just don't, I'll give you the reason as those come about, just on a few. Okay, so.
I have a quick question.
Yes.
Sorry, just where did you post that sheet that you just went through?
I posted it late. I just posted it yesterday. So so it's just with the activity. I think I posted it with today's activity. If I go down to, you can see what I'm.
Okay.
Yeah, so it's here, the practice problem.
Okay, cool. Thank you.
And I just did it yesterday. I was looking at the activity and going, oh, there's not enough here. Added something. Okay, so this one, we already have this in S-cis. That's good. There is an internal plane of symmetry here. I don't need to concern myself with regiochemistry. And the electron withdrawing group is pointed in, so we know that's going to end up down. So as we draw that, nothing is arranged. I'll just cyclohexene.
Dr. Gilly, I don't know if
Yes.
it's me, but we can't see what you're doing.
Oh, may not do. What did I do? That,
Okay. That helps a lot.
yeah, thanks. I sometimes like just switch over, like click over and didn't actually share it. I mess myself up sometimes. But I make other videos on Zoom, and I like ruin the whole thing.
No, you're good. Online teaching seems really tough.
I know it's hard because I can't see what you guys can see.
Yeah.
But a lot of people put like a little second screen so that they make sure, but I'm not savvy enough to do that. Okay, so we are going to start with our cyclohexene. I've got 2 methyls on the 2 ends, and because there's 2 of them, those 2 carbons don't become a chiral center. So don't worry about it. And the only one that is going to be is this one, right? And my little aldehyde pointed down because it was for the endo. And because I have at least 1 stereocenter, I will also get the enantiomer. Next. So
Can you go through that again, but slower, and remind us again? Okay, so these are in. This one's up of the dyne. I feel like that was
Okay,
a little
so
fast
this is,
for my brain.
yeah, this is our S-cis, right? So that's step 1 completed. And then if I think about how I'm going to combine these in the cyclohexene ring, I would number them something like that. And the only pi bond that's left ends up between 2. So at carbon 1 and 4, there are 2 methyl groups attached to each of them. So I make sure that my 2 methyl groups are drawn in at carbon 1. So anytime you have a non-hydrogen group, Then here, we're going to be forming a bond between 5 and 6. 4 forms a bond with 5. 1 forms a bond with 6. That's forming the ring. And then 6 has this aldehyde. And it will prefer an endo approach because of favorable secondary orbital overlap. So that means it ends up down that carbon. And because I have one stereocenter, I have to write plus an H because it's possible that this diene approaches from the bottom and from the top. Next one, we're going to look at the diene, and we see that it is given to us in an S trans. So we have to do a little flip. So you can do, just draw it again. Then we ask ourselves, can we find a plane of symmetry in either the diene or the diene file? So this is step 2. I cannot, right? Because there's no symmetry here. If I chop this alkene in half, there's no symmetry. Which means I have to care about Regius. So from drawing out resonance contributors, I'm going to note that this carbon is delta negative. And this carbon is a delta positive. So this is actually aligned. Maybe I'll draw this over. Weird how it looks. So right now we are so right now I have my delta negative aligned with my delta. That's good. So this is the correct alignment that I need to make sure. I also, you might have noticed I flipped the methyl and the methyl ester. And that's because this is the electron withdrawing group. So it needs to point endo. That's why I flipped it over that way. So now if I draw my product, and I didn't leave much room in there for numbering. So with the diene part, that ends up with these 4 carbons. The alkene ends up here, and the only substituent on the diene is this methoxy, which is here. And because it's on an interior carbon, it doesn't end up on a dash or wedge. Worry about that. There are no substituents at these carbons in the diene, so there's no substituents. The only other carbon that has substituents is this one, which ends up being this one. So we have a methyl and a methyl ester, and one of those needs to go on a wedge and the other one needs to go on a dash. And we know that the group that points endo, the electron withdrawing group, that ends up there. So on the wedge, sorry, the dash, but the ester. That means that my methyl group. That's the only stereocenter, is that one stereocenter. But just one is enough. Follow that one, Shira, is that okay? All right, so moving on to the next one. The diene is given in S-cis conformation. So moving on to step 2, I'm looking for an internal plane of symmetry. I don't find one, so I have to care about the charges, partial charges. Through resonance, I can end up moving the lone pair on oxygen all the way down to bottom carbon. And the positive is always furthest away from the electron withdrawing group. So these are actually nicely aligned already. We don't have to do any flipping, right, because the alignment is already correct. That's helpful. Because this is a ring, I'm going to end up with a bicyclic structure. I will end up with a 6, 5. Sometimes it's easier just to sketch it in without stereocenters first and then worry about the stereochemistry. So without worrying about stereochemistry temporarily, we get something like this. So the only carbon that had substituents is this one, and then this as well. And now, how many stereocenters do I have? Right? So when I draw the final product with stereochemistry, I need to have dashes and wedges for all of them. Notice that this is the electron withdrawing group, the orbital here. It needs to point in, which means these bonds are going to be down. So when I have the stereochemistry included, I draw those. They're both down because it's part of a ring. So if one is down, the other one has to be down. And up here, we just look for the positioning. Anything that's in, like this methoxy group, here, ends up. Find the methoxy group up here. That methyl that's pointed out right now is up, down. Don't forget that. This is the answer with stereo. And as long as you have one stereocenter and no internal plane of symmetry, there will be an answer. So moving on to this one, our diene is already in an S-cis conformation. That's good. I'm looking for an internal plane of symmetry. I did find one in the diene file, so I don't need to worry about regioselectivity. And I can start sketching in the product. Okay? And again, I've got 2 rings now. So this is going to be a bit of a challenge to draw. Now we're forming a 3rd ring. 2 structures that already have. So remember that this one, we kind of sketch in, start like this, and then I have a 2-carbon bridge here. So I do a 2-carbon bridge. And I know where my alkene ends up. That in. Then I have, I'm attaching now this 6-member ring. So I usually come down here for the attachment. This is already part of a ring where these are going to be endo. So they're going to point down. This is going to be a bit of a challenge because we have to basically have a 6-member ring. Hydrogens here, those will point exo. So these ketones will be endo and they'll end up down. The hydrogens will be exo and they'll end up up. So sometimes drawing those in to see the groups that are pointed out. So basically you flip this. It needs to be an endo approach. So it really approaches more like this. Endo, electron withdrawing groups endo, and the hydrogens here exo. So it doesn't really approach this way. It approaches this way because these are my electron withdrawing groups and they need to approach hydrogens would be extra. Okay, the only thing I forgot to add so far are the substituents of those two carbons. There, you can just show those in this direction, dimethyl. This one is a bit of a challenge. There are chiral centers here.
What does the plane of, I'm getting a little bit confused with the plane of symmetry and what that affects.
Okay, so when you have a plane of symmetry, you don't have to worry about delta plus and delta minus. Because imagine if they approach this way as drawn, and then you flip the one with symmetry over and you have it approach, it's no different. So like up here, when we didn't have the plane of symmetry, we had to carefully consider where, if there was a delta, negative, and minus, and make sure that they're aligned. And if they weren't aligned, I might have to flip one of them over so that they were aligned. Whereas down here, because we had this plane of symmetry, it doesn't matter. Like I flip this over, it's the same thing because of the plane of symmetry. So I don't have to worry about, oh, is it the right approach or do I need to flip it over? It doesn't matter. Flipping it over is the same thing.
For the substituents that are on like the bridgeheads, does it matter how we draw those in? Because those are chiral too, right?
Right. And it just works out because, okay, I know it's very confusing. Think about the diene over here. Think about the in and the out, right? So these two are in, right? Whereas over here, these groups are out. The dimethylamine is out. So remember we said the in groups end up, right? If you look at these bridgehead carbons, what's up? Right? What's up is literally that bridge. Pointed straight up. So the groups that were in, they are ending up. So it's correct to draw it this way. Whereas relatively speaking, the methyl and dimethylamine are going to end up down, and these are down in space compared to, see that? This is like a, in became up, and then these became, outs became down. So if you draw it the way I drew it, it has the correct stereochemistry. And it's confusing on the bicyclic ones because we don't draw dashes or ridges. Just the structure in and of itself already gives the stereochemical information without a dash or ridge. So, moving on. So here's one where I'm going to I'm debating whether I should just not even deal with it or actually. So I think what I'm going to do is for the first one that's like this, I will go through it for you. And then after that, I'm just going to cross them out because you're not going to see that on me. Okay. But I just want to explain why my answer is going to be different and like what sort of thing am I talking about that you don't see. Okay. So if we're looking at the diene here, first of all, it's in an S trans. You need to flip it, right, to an S cis. Notice that this is E. So I want to make sure that as I flip, that it remains E. I need to convert to an S cis. But look at what is the electron donating, right? It is a alkyl group. If you noticed from before, our electron withdrawing group always had when we needed it, right? So like in this case, there was symmetry. So But over here, it's always an oxygen with a lone pair, right? Oxygen with a lone pair, or maybe a nitrogen with a lone pair. Over here, we're just looking at a tert-butyl group. Are alkyl groups, such as tert-butyl groups, electron donating? Yes, they are, but not through resonance. They donate through something called hyperconjugation. It's kind of like similar to induction, not exactly. So they're weakly electron donating, very, very weakly, not strongly like oxygen. That donates strongly through resonance. This only donates really, really weakly and not through resonance. So I would argue that there is no, even though there's no plane of symmetry, there is no delta negative carbon. Neither one of these is that much more electron rich together. And there's certainly no resonance contributors to -1 is delta negative. So as a result, you're not really going to get any selectivity. So if neither one of these is delta negative, then it's impossible to align it perfectly with this delta positive. Which means there's going to be no preference in how it approaches, and you would end up with a right? So if it approaches, and there's no plane of symmetry, which is why we have to observe the approach. If it approaches like the way it's shown here, what would that give us, right? That would give us a tert-butyl group down here. Since it's pointed out, it's going to go down. And we have the nitrile here, the CN. It's endo, it's also. But it's also possible we flip the dienophile over and it approaches from the opposite relative orientation. The cyano is bottom here, top. So that would change where the cyano ends up. Potentially end up there as well. So these are the two mixture of constitutional isomers, also known as mixture isomers. And I don't think there's a preference. You're going to get a mixture. So I think you get a mixture of basically 4 different stereoisomers. Those and their antigens. So in a situation like this where the electron donating group is an alkyl group, right? We're not going to see. Yeah, because it's just going to be too many products. So when I come across those again, I'm just going to cross them out. So I think it's just better not to use examples like that, especially when you give a good products. Okay. So moving on, we're at this next one here. We're already in an S-cis conformation. There is no plane of symmetry, so I do need to consider where the delta negative and delta positive are. That comes from the resonance contributors. Sulfur is okay as a donator because it has lone pairs like oxygen or like nitrogen. Right? So it would donate just like an oxygen would, all the way down to this carbon, making this the delta. And right now, it is not aligned with the delta positive. So we have to flip one of those over. And in addition, we also have to draw a bicyclic product because of the fact that this is part of a ring. Okay, so we are going to note that instead of this approach, it's going to approach with this group called A. Basically going to approach endo, and I have to flip it so that my delta negative and delta positive are in alignment. Okay, so we get to have fun drawing this bicyclic product. Remember, I kind of always start out with something like this for these 4 carbons. I'm going to have this interesting 2-carbon bridge, the top for those 2 carbons. And then it's also attached to a 6-numbered ring. We have our alkene here, forming a 6-numbered ring. And the sulfur ends up there. And what did I add? Right, I added this dienophile. It's got the electron withdrawing group pointed down. That's the CO2 or A. And then the methyl pointed up. Because the methyl approached exo, so it ends up. Electron withdrawing group approached endo, so it ends up. This is just a CH2. Definitely have it in here. I'll try not to get this crazy. He likes to do some challenge. Okay, so we have the diene in this one as cis already, so that's good. They actually both have an internal plane of symmetry. That's fine, that's perfect. We don't have to worry about regiochemistry. We just need to sketch out the product. Since the diene is in a ring, we need to draw a bicyclic product. And this is also part of a ring. We end up with this 1-carbon bridge up here. And I've added this 6-numbered ring. These, of course, are going to, carbonyls are going to approach endo. So instead of approaching this, it would really approach the carbonyls endo. And as a result, they end up down hydrogens here. I like to kind of draw those. Orientations are going to be up. Oops, I forgot my double bond. So this one, right, ask yourself, does it have an enantiomer? It's tricky. The answer is no. And that's because you can slice it in half. Imagine kind of like slicing it right through this methyl. There is an internal plane of symmetry that's difficult to draw on paper, but it happens when you've got this totally symmetrical situation. Oops, sorry. This is meso. It has an internal plane of symmetry. Are there chiral centers? Yes, but they're completely canceled out through an internal plane of symmetry. Meso, it does not have an enantiomer. Meso compounds are achiral, even though they have chiral centers. Well, you heard the term meso. Okay, I don't hear anybody stopping me. I'll keep going. Kind of running out of time. I can speed up a little bit there. And you can just kind of watch this later if I'm going too fast. And in this case, as cis, there's planes of symmetry, so you don't need to worry about that. We have a triple bond here, so we're going to end up with a 2 double bonds. And the only groups that are substituents are these 2 methyl esters. And these carbons don't end up as chiral centers, so you just draw regular lines. This is a meso compound. So again, does not have an enantiomer. This one, the internal plane of symmetry is. Okay. Over here, we already have S cis. Oh, you know what? I said I was just gonna not worry about that because this is where the donating group is an alkyl group. Right? We're not gonna do that. It's just gonna give a mixture.
Question about the one you just went, the top one. So on his key, he doesn't have two double bonds, but the two double bonds is correct.
Yes.
Okay.
Isn't it bicyclic? Or no?
Oh my gosh, right. So you could kind of draw it like this, or better to draw it the bicyclic way. This two double bonds. And it is still.
And why on that one do we not care about the up or down, endo, exo, like the stereo?
Okay, because these carbons are sp2, and so they're trigonal planar, so there's no dasher wedge. We only do dasher wedge when it's sp3.
Okay.
And this one, so this one already given to us S-cis, but there's no plane of symmetry, right? So we have to figure out where's the delta negative or positive. In this case, right there, those are not aligned. So we would need to instead draw this pointed, so flip it over, and then make sure to keep the nitro group pointed in because it should be in. Now it forms a cyclohexane ring. There is a methoxy group here because it's pointed in, ends up. And then there's a nitro group at this carbon, and because it's pointed in, endo. So this was important that we have the correct alignment because there was no. Looking at this, we have a S-cis conformation. There is no internal plane of symmetry. So we need to figure out where is the delta negative and delta positive. So the nitrogen has a lone pair that will push electrons up here to make this delta negative and positive. So these are also not correctly aligned. So we need to flip this over. But we'll make sure to include that electron. Make sure it stays. Now, as I flip this over, my opposite charges will be aligned. This is going to be bicyclic. Start sketching it out. There's a 2-carbon bridge here, so that's why this is 2-carbon bridge. Double bond up here. Dimethylamine there. Again, this carbon stays sp2, so it's a regular line in the dasher wedge. Then the only other group is this sulfonyl group, the electron withdrawing group, and it approaches endo, so it ends up there. No internal plane of symmetry there, so so this one, the diene right now is in an S trans. And it's not, doesn't really look like it should in terms of how it typically looks. It's sort of drawn, sort of going up and down, left and right. So we just need to change that. So we're going to do something like this. If we group the diene. So it looks more like the and there is no internal plane of symmetry on either the diene or dienophile. So that means I have to make sure charges are aligned. They currently are not aligned. we would have, this is the alignment here. This is not. That would mean I have to switch one of these. So I'll redraw it over here. Typically, we flip over the dining file by convention. So I'll just make sure that's over. So that now I have perfect opposite charge. Sketching my focal ring, methyl amino group there, and then the down electron withdrawing. Going quickly, you can always watch it back or let me know if you want me to stop and go slower. The diene right now is S-cis, so that's good. There is no internal plane of symmetry, so I have to consider partial charges. The sulfur lone pairs will push electrons all the way to delta negative down here, and my delta positive there. So technically these are in alignment. The problem is that I want to make sure this really should be endo. So you might want to redraw it. Have to if you can kind of visualize it. If I redraw it, I'll keep the diene looking the same. And the alignment is correct. It's just that I want the electron. But just because I flipped that over, I still have the correct alignment. That's good. This is going to be a bicyclic product. I'll just start there with my 2-carbon bridge. And putting these in quickly. The electron withdrawing group ends up pointing down. Endo, the methyl will be up. For this one, I might add in some hydrogens just for clarity. Hydrogens here and here. Here. Now the super challenge intramolecular one. So we have diene is already S-cis. There's no plane of symmetry, so I've got to compare my charges. Delta negatives here, delta positives here. These are aligned. Okay, and my electron withdrawing group is pointed endo, so I'm happy with that as well. So we just need to start sketching out the product. So we have the formation of a 6-membered ring. I always kind of start there. Okay? And alkene will end up with those 2 carbons. This methoxy is pointed out. So it ends up down. And the methyl ketone is endo, so it also ends up down. Then I just need to see, okay, maybe some counting is in order here to help us kind of visualize. 1, 2, 3, 4, 5, 6, 7, 8, 4. I know this is carbon 10, carbon 9. So I'm making a bond between 4 and 9. So I just need to have all those additional CH2 groups. So carbon 5, carbon 6, carbon 7, carbon 8. So 5, 6, 7, 8, attached to 9. And let's see. We have some more stereochemistry to add that I did ignore at first. This is pointed out. Bond between 4 and 5, so this will be down. And over here we have, this is a cis configuration, so they're both pointed. Super challenged on that one. So kind of maybe I'll do some. This is out. This group is out. That's why they both end up down. Down. Okay, and then this group is endo. Endo. They both end up that helps. Okay. So Shira, I see, is here now, and I know she wanted me to go over this problem from last time. Let's go over the mechanism so you can visualize how this forms. You want in, Cam? Let's look at the mechanism. So we're starting out with the diene, and we're treating that with HCl. So the first step is a proton transfer, and it always occurs at the terminal carbon. The pi bond picks up the proton, and the hydrogen regioselectively will go on the terminal carbon. And I'll show you why it does that. The hydrogen ends up here and not here. Because if we put the hydrogen on the terminal carbon, so one of the terminal carbons of the diene, then the carbocation goes on the other carbon. Now it's a Lilic resonance stable. So we can draw out the other resonance contributor, which is formed from shifting. So those are our two allylic carbocations, resonance stabilized. The partial charge is really shared between these two carbons, which is what the resonance tells us. So the chloride that was formed from the first proton transfer step, that chloride, it can attack either carbon that has a partial positive charge. Either attacks this carbon or it attacks the other. That leads to two different products. Both of those carbons have a partial positive. And if it attacked this carbon, get this product. If it attacks the other carbon, so it's the placement of these. I call this carbon number 1 and that's carbon number 2. I call this carbon number 1 and this is carbon number 4. Okay, so it's the placement of those that tells you if you're going to call it the 1,2 adduct or the 1,4 adduct. And the 1,2 adduct in this case is the major product regardless of what temperature the reaction is. If you heat it, if you cool it, it doesn't matter. This is the major. Because the 1,2 product always forms faster. It is the kinetic product, so at low temperature, it's trapped faster in the major product. But this also happens to be the thermodynamic product because the alkene is more substituted. This alkene has 3 carbons attached. So if you're looking at these 2 carbons, how many carbons attached is that have 1, 2. We say this is tri-substituted. Whereas over here, we're looking at these 2 carbons. There's only 2 carbons attached. This one is di-substituted. This one is tri-substituted. The more substituted an alkene is, the more stable through hyperconjugation. And so this will be the more stable product, meaning it's the thermodynamic product and it's favored at high temperature. So in this case, the 1,2 product is major at both high and low temperature, because it's 1,2 is always formed faster at low temperature. And in this case, it's the more substituted alkene, so it's more stable, so it will form as the major product at high temperature, where it's an equilibrium control reaction. Does that make sense, Shira, or can I answer any more questions?
Yeah, that's good. Thank you.
Okay.